Hello everyone, welcome to PCB Workshop. Before we begin, download Kicad. It's an open source PCB design. And also download UltraLibrarian. UltraLibrarian is going to ask you for a company name, so just specify Virginia Tech and then put in your VT email and it should let you in. Okay, so just a little bit about myself. Here's some PCBs that I've designed over the years using Kicad. I'm a master's degree student at Virginia Tech. I'm taking electrical engineering with a specification in control robotics and autonomy. These are some PCB designs that I've done for working for a small military contracting company. Kicad is very capable PCB design software, and you can create anything you'd need to for a senior design project or just low volume prototyping. But it's also useful in company scenarios, and you can use it in industry. So these slides are going to cover a brief introduction of preliminary stuff that you should know about Kicad. The goal of this workshop is you should understand the workflow of Kicad. You should know how to design custom symbols and footprints, apply net classes and basic design rules for routing, and at the end you should have a completely designed PCB ready for manufacture. And you can use this design file that we're going to create in this workshop to be able to import all the design settings into your newest project, so you don't have to go through all the changing settings step. We're going to be using Osh Park for our manufacturing and all of our board constraints, so keep that in mind. So what is Kicad? Kicad is an open source PCB design suite for schematic capture and layout. It gives you a lot of design tools, and it's completely open source, so you can get it for free and pretty much run it on any computer without any trouble. It's a pretty powerful tool. It contains a schematic editor, footprint editor, PCB editor, and 3D viewer. The schematic editor, you can actually run SPICE simulations on it. I've never done it before, but it is baked into the system, so you don't have to use a separate system to run SPICE simulations. You can test it there. I personally like to design all of my boards on breadboards before moving forward with the design and making sure everything's functional before I have a final prototype. Kicad allows you to export Gerber and drill files and pick and place files for PCB manufacturing for assemblies. You can essentially design everything in Kicad and export all the design files needed to ship it to a PCB manufacturer and have them make it. And we can also view these files that they're viewing to double check that all your file designs are great. The Kicad community is very large and offers a variety of different plugins to expand Kicad. I used to have a Kicad plugin that essentially outputted all the pick and place files for Kicad, and it formatted it in the specific format that JLC PCB manufacturer required. So instead of making my own Excel spreadsheet, Kicad did all of that for me. Okay, so what is a PCB and what is it made of? So basically a PCB is just a sandwich of copper layers and PCB dielectric. The dielectric is typically FR4, which is a fiberglass. And in between these copper layers, you run these traces. So they cut out these traces which operate as your wires on your board that make connections between your different components. And then we have vias, which are interconnections between these different copper layers. So if we wanted to run a trace from this via to this via, then we could actually use a via to go under to our bottom board layer, run a trace, and then pop back out with another via right here and make this connection. This gets more extreme with more layers that you have on your board. In our example, we're only going to be dealing with 2-layer boards, but with Kicad it is possible to do as many board layers as you need. So on top of the fiberglass sits solder mask, which is basically a layer that prevents solder from sticking to the board. And on your footprints, which are the actual cutouts in the top layer that specify where you're soldering your components, there's holes in the solder mask so that you can solder on to the actual copper pads and make a good connection. There's also silk screen, which is your markings on your board. It's this white seen on the left. And these markings allow you to know where your components are sitting, so that when you're doing diagnosis after the fact, you can tell which resistor you're dealing with. If you need to replace a part, then you don't need to pull up your PCB design specs to figure out what this specific part is, because you'll know it's R4 or C4, whatever capacitor that you specified. So some board layer designators in Kicad. FCU and BCU are front and back copper layers, which are what we're going to be using for our example. F-Silk is your silk screen layer, which you can put text and you can specify component outlines. This is particularly useful when you're laying out ICs and you can specify where pin 1 is so you don't accidentally solder on an IC backwards and short it. F-mask and B-mask are your previously discussed solder mask openings. So if we put solder mask over our pads, then it wouldn't be possible to actually solder onto them. So fortunately Kicad does this for you, but it leaves holes for your vias and your actual footprints so that you don't need to specify where the solder mask holes are. Edge cuts, this one's really important. This is your board outline. This is the actual shape of your board. You need to talk to whoever's designing step files for your project. If you're going to mount your PCB, then you need to know the specific shape that your PCB has to be. F-paste and B-paste is your stencil data. So if you have SMD components, surface mount components, then you're going to need this F-paste and B-paste in order to get actual stencils so that you can lay it on top of your board and apply solder paste for surface mount components. In one are interior copper layers. So if we're going more than 2, then we can specify these inner copper layers. And mechanical are just for the PCB manufacturing companies. These layers are all color-coded so that you can easily see which layer is which when you're actually laying out your PCB. So before you actually design your PCB, we have to actually make a schematic that represents the PCB, and it maps all the connections between your components before you actually go to lay everything out. When you place these different ICs, you need to have an associated symbol that represents the IC, and you can get these symbols from open source libraries. Specifically, we're going to be using Ultra Librarian, but you can also make your own symbols from the datasheet, and we'll be doing that. It's important that you define the pins that they're associated with the pins in the footprint, so you don't accidentally specify all your pins, and then when you go to lay out the footprint, they're completely mismatched, so they don't line up. And this makes sure that you're actually hitting the pins on your IC that you need. Include any metadata, and organize into symbol libraries so that you can get easy access later. If you're going to be reusing an IC, then it's important to organize your libraries so that you can actually find it when you go to make a different project. Say if you have a favorite microcontroller, then you can put it in your symbol library and look it up and just place it when you need, so you don't have to reinvent the wheel every time you need a symbol. And utilize web part libraries when needed. There's no need to reinvent the wheel and design these symbols, because typically someone's already designed the symbol for you. Footprint design. So footprints are your actual physical layout of the chip that you're using and how it solders onto the board. So this is the copper pads exposed to actually interface from your PCB to the chips you want to solder on. You have to specify pad size, shape, and drill holes for soldering and mounting. And you need to look at the data sheet and the mechanical diagrams to actually draw out your shape and make sure everything lines up when you go to solder it on. These include courtyards, and courtyard is basically a keep out zone around the IC that doesn't let you place parts within other parts. And then utilize silk screens to make sure that you have good references, so you know, like U1 is associated to a 555 timer, or this resistor is R1, this resistor is R2. IPC compliant pad spacing. So IPC stands for International Printed Circuit Board, and it's a standard that makes sure that you're actually getting good solder contacts. These are really important for very high quality PCBs to make sure that you're making good solid connections so that you don't have unnecessary impedances in between your connections. Make sure you add pin 1 markers so you know the orientation of your IC when you go to solder, and organize your libraries. So these are some footprint and symbol libraries that I've used. Today we're going to be using Ultra Librarian, and hopefully you've already made an account. You can figure out which parts you're going to be using when you go to lay out your schematic, and I would add descriptions with all your parts with links to DigiKey or wherever you're buying the parts. Then you can take that part designator, the part number for it, and then look it up in Ultra Librarian, and then you can get your footprints and symbols for the specific parts without having to go through the trouble of looking at the mechanical data sheet and making it yourself. It saves a lot of time. So vias and traces. We've previously discussed this, the picture of the PCB, but these are just brief descriptions of what they are. Traces are copper connections between component pads. Their size depending on how much current you're pushing through them. So if you've got a power trace that needs to supply power to multiple ICs, then you're going to want a larger trace. If you just have a small signal trace that is just carrying a very low current signal, maybe we're talking about a USB connection, then it can be very small, and you want to just make sure that it's small enough to actually fit onto the pad if the spacing is really tight for your pitch. And I'm gonna give you a bunch of predefined track widths so that you can utilize them when you're actually laying out your PCB. They're pretty handy. Vias are in between connections between the different copper layers on your board. If you're going to go around a trace, you need to make a connection and then there's a trace in the way, then you can use these vias to go around them. It's a good idea to keep your traces as short as possible, and you use the minimal amount of vias to keep your impedance down and just get rid of any weirdness in your board. There's 3 different types of vias. There's through-hole, blind, and buried. Through-hole vias are ones that are just exposed on your board, and you can solder onto them, and you can see through the actual board. Blind vias are kind of like through-hole vias, which go through the board, but they're covered in a solder tent, so you can't actually solder onto the pad, and you can't accidentally short them because they're completely covered, and you can't typically see through these. Buried vias are vias in between your internal copper layers. If you have like a 4-layer board and you had a via in between layer 2 and 3, this would be a buried via. And similarly to traces, if we have high current, then we're going to want a larger via to accommodate for that. So these are just some design philosophies that I've learned making PCBs over the years. Keep it simple. Try to minimize the amount of parts you need and passive components to keep your board footprint small. We want as short as traces as possible and as few vias as possible, and try to use the minimal amount of layers possible. You can use fewer layers if you group your passive components by the IC and like functionality. If you have like a small subsection for charging like a LiPo battery, you're going to want to keep all the capacitors and resistors associated for that LiPo charger right next to the chip itself, and then you want to make those connections localized, and then you can take that connection and actually connect it to whatever subsystems need power. And this makes sure that you don't have to stretch a trace across your entire board because you put the resistor all the way across. And we're going to be dealing with something called ratnets, and ratnets are these little blue lines on your board that specify the connections you need to make, and it's important to detangle all these connections when you place your components out before you make your traces to minimize the amount of vias you need. Avoid sharp 90-degree turns, use 45-degree turns. This doesn't matter as much for low-frequency applications, but for high-frequency applications, these sharp 90-degree turns kind of act like open connections, which is kind of messy when you are doing high-frequency stuff because it basically makes an antenna, and you don't really want an antenna on your board if not necessary. Follow manufacturer layout guidelines for ICs. So some ICs will specify that you place passive components super close to this pin and you make the trace very short, and they'll give you actual pad layouts for the chip, and it's important to use their design specifications because they've done all the math, all the testing to figure out the best layout that gives the IC the best performance. So scroll through the data sheet and make sure that they don't have any like specific design constraints, and if they do, then follow them to a T. This is common with like buck converters or boost converters where they want the boost capacitor to be very close to the boost pin to minimize impedance, and that to keep out jumping on that specific pin and to keep your power quality as high as possible. and decouple every IC. So for every IC you use, it's a good idea to place a little like 10 microfarad capacitor right by the power supply of the chip. And if you do this to every chip, it essentially gives every chip a little battery pack. So if the chip has like a super high current demand, then it'll just drop from the capacitor, and this prevents you from like dropping the voltage bus on your entire board, so you don't brown out any of your other ICs. Ferrite beads. Ferrite beads are really important for high-speed signal lines. It works as a high-pass filter, and it essentially gets rid of like super noisy, or not a high-pass, a low-pass filter, and it gets rid of any noise on that signal line that might interfere and give you corrupted data. Differential pairs are impedance matched traces for high-speed interfaces. So USB, you'd use a differential pair, and this matches the impedance so that the signal is as high quality as possible when you actually go to the chip that takes in the USB. And this makes sure that they're the same level and one isn't more attenuated than the other for when they use a comparator against them. So thermal management, on your some chips that take in a lot of power, they emit a lot of heat, and you can use vias to spread out the heat signature of the board or the chip, and you can use the PCB as a radiator. So if you use a bunch of thermal vias, which are just vias intended for heat dissipation, you can spread out the heat signature on both copper layers so that the IC can vent excess heat to the PCB and spread it out. DRC stands for Design Rule Checker. This is going to be your best friend with PCB design. This makes sure that the board that you designed is actually manufacturable and doesn't violate any of the manufacturer's design rules. It's a good idea to check this pretty frequently to make sure that you're not violating any of their rules. And it's better to catch mistakes early so that you can fix them, so that you don't have to relay out your board if you accidentally make a single mistake. And utilize silk screen labels so that when you go back, you can pull a pin off and make sure, if you're like testing a pin and it's important for your prototyping, then you can label that pin so you know what that actual signal is, so that you don't have to pull up all of your board design files every time you want to like connect something up. Like if you're testing a boost converter and you wanted to test the output, you can label the output with the silk screen label, so that instead of looking up your PCB design files to figure out which one's V out, it's already clearly labeled on the board so you can test it. So quick workflow recap. Hopefully you have Kicad installed. Make an Ultra Librarian account. We're going to open Kicad and make a new project. We're going to use symbols in Kicad's like open source library to design our circuit. We're going to utilize net classes, assign footprints to all of our symbols in our schematic. We're going to import components from our schematic onto our PCB workspace. We're going to define our PCB edge, the general shape of the PCB, depending on how many components we have, or if you have a specified shape in mind. Then we're going to design our PCB using our footprints, traces, and vias, verify that everything looks good with DRC, Design Rule Checker, and create drill and Gerber files for manufacturing. So these are your board design rules that we're going to be putting into our settings. In Kicad, I got these directly from Park's manufacturing website. If you're using a different manufacturer, then you have to use their specific design rules, and typically they have design rules that you can plug straight into Kicad. These are predefined trace and via sizes for you guys to use in your board setups. So for fine traces, very low current traces, we go with 6 mils, and then we just go up from there. So for high power and ground, we use a 50 mil trace, and then the in between. For standard traces that don't require a lot of current, you can use 12, but typically it's a good idea to use as big as a trace as possible to keep your impedance down. And I would go as small as you can to actually get a trace onto a pad with like a super small pitch. If you're dealing with like a super high pin, small pitch microcontroller, then you'd probably have to use this 6 mil. But if you can, use this 12 for medium signals. And then there's specified pad diameters for your vias and your hole diameter. The pad is the actual exposed copper bit that you solder onto, and these are the associated vias for the different trace sizes. Now you can go online and use specific online tools to figure out what size traces you need for your current and power consumption that you're using for a specific line. Those are just some good to have predefined traces that'll work. But if you have like super high power requirements or you're worried about it, then definitely go to the online checker and make sure that your trace is going to be good. So net classes are labels that you can use in your schematic to define different connections on your board, so that when you go to route them out on your PCB design, you don't have to specify each connection individually and keep track of which line's a power line and which line's a signal line. You can predefine them in the schematic, so you can just route them out without any extra trouble. And we have the associated rules with all of these. So these are just some steps to order with Park. We do a final DRC to make sure that our design's good, we're not violating any rules, there's no errors, all of our connections have been made. We export our Gerber and drill files, and then we zip that up. To export the Gerber and drill files, we go to File, Plot. This opens up a pop-up. You specify the output directory. Just make sure that the output directory is the same for your Gerber and your drill files. And just generate both sets of files. And as previously said, zip them up. Submit this to Park. And double check in Park's website that your PCB looks good, and then you can order. Okay, so hopefully you have Kicad installed and have an Ultra Librarian account. This is like Park's website defining all your design rules for Kicad. So this is where I got all the design rules. So with that, we're going to start our example. So to start, let's make a new file. So let's start a new project. can name it whatever you like. And then we can double click this right here to open our schematic editor. And this is our schematic where we're going to actually be drawing out our circuit, and we utilize the symbols for each of your components. If you have a really complicated schematic, then you might run out of space on this sheet, and you can change the size right here in the page settings, make it slightly larger. You can also add in additional sheets if you want to keep like a standard page size. Okay, so to start, we're going to import a specific capacitor that we need to use for our circuit. We're going to be designing a simple 555 timer blinker circuit. So we're going to be using this capacitor. So look this capacitor up in DigiKey, or you can just like type this straight into Ultra Librarian. So go to Ultra Librarian, search up our part, and right now we're downloading both the symbol and the footprint for this part. So we can see right here, here's the symbol, here's the footprint. Everything's been designed specifically for this capacitor. You can do this for every part in your schematic, or you can use the the Kicad standard libraries. So download now, and then Ultra Librarian provides Kicad format, so just specify whatever version you're using. I'm using the newest version. So we're going to download that zip file. And then just unzip it. And then we're going to import it into our Kicad. So select up here. This opens up your symbol library. We're going to create a new library. We'll make it global. If you were only going to use this part for this specific project and you don't foresee yourself using it for other projects, then you can make this library specific to this project, but it's a capacitor and it's a standard size, so we'll just put it in global for now. Here you can specify where you're going to save it at, the library that is. You can save that whatever. I like to put it in a file I named Kicad library. And we can just name it that, the actual part. Okay. And then with this library selected, we're going to go File, Import, Symbol. And then we're going to navigate to our unzipped part library. And then select this file, load it in, and here's our part, our actual symbol. Save that. And then we can import this file in by selecting Place Symbol. Search it up here. Here we go, that's the library we just made and the part. So double click that. You can rotate parts with R. place it anywhere in there. Also make sure that we're using the positive side and which pin that is. So from this we can see pin 1 is the positive side, so we need to keep that in mind when we design our schematic. Okay, so next we're going to be adding in a 555 timer. We're going to be using this ICM. We'll go with P because it's going to be the PDIP package. Place that down. Next, we're going to want a power interface to actually power our board. Just look up connector. I'm going to go with this 1x2. Connector generic. Hit R twice, flip that thing around. You can select on the component and we want to mirror it, not horizontally. Mirror it vertically to get pin 1 on top, because I was going to make that our 5 volts. Hit this little ground symbol to put in our power symbols. So first we'll put a ground. Always put your grounds facing down and your power symbols facing up. I'm using 5 volts. You can use whatever you want for that. And then we can hit this right here to place a wire and make that connection to our symbol. You can also just click on these little pins right here to connect them. Okay, and then we're just going to fill out the rest of this. We can put in an LED. We're looking for this 5mm, and this one's nice because it just gives us a 5mm footprint. So just because we're not using like an IR LED, we can use a standard 5mm LED and it gives us a footprint right here. So just double click that. Place that down. Hit R to get your resistors. And just copy and paste it a couple of times. There we go. And then we're just going to make the rest of our connections. Oh, first we need a power for our chip. And the ground. Make sure that you're using like the same ground. So if we go in here, we can see all these different options. So if we use like 5C, it's going to be a whole different net, and you might have issues laying out your power. Because if you put like the 5C one up here, then it might not specify that you need to connect it to this, and you might not get power to your IC if that connection is not made. So next, just make your connections. What we did with the capacitor earlier, you can do for any part. So if you were using a 555 timer with like a specific pad layout and you want to buy it and you found the part on DigiKey, then you can take that part number and do the same thing we did for the capacitor to import the symbol. You can also make them, which I'm going to show you later. Okay, I'm just verifying that all the connections I made are correct. Okay, so that looks good. So next we're going to be specifying our footprint assignment. I'll make sure you save your schematic as well. Okay. So let's open up our footprint libraries and we're going to import our footprint that we got for our capacitor earlier. Oh. I'm just going to delete that. Copy that. Okay, and then we're going to import Kicad file. We're going to go to our unzipped file that we downloaded earlier. And it's going to be footprints.pretty. Actually, let's rename it really quick because I've got existing ones. You shouldn't have to rename it though. Here we go. Oh, we can just go in here, select that, hit OK, and then it should import your footprints. That's an error for something else. Okay. Oh. Oh, that's weird. Okay. So So right click on this, view selected footprint, and then we can verify that our footprints all look good. Okay. So here's our imported footprint for our capacitor. This is sized specifically for the capacitor that we want to use. Our previously selected 5mm diode. Okay, for our connector, we're going to be using connector pin socket 2.54, which is like a standard pin header so that we can solder onto it and supply power. There we go. So we're going to be using that one. Just double click on it to assign it. Okay, for our resistors, we're going to go over here, resistor through hole, and then I already did this and measured it out, but for every component that you're going to use, double check in this footprint viewer to make sure that it's actually going to fit your component. So I sized everything out for the 1/2 watt, and they actually specify in the description what the wattage is and what the size is. So this is a 1/4 watt resistor, but even with that, you're going to want to double check, measure your resistor, and make sure that this is actually going to fit. So for us, we're going to be using the 9mm 1/2 watt. There we go. So 1/2 watt, super long, plenty of space. Double click that one, and just keep double clicking it for all your resistors. Okay. And that's all your footprints assigned, so just save that. Apply to schematic, hit OK. And then open your PCB editor. Okay, so the first thing we're going to do in this space is click board setup, and then we're going to specify all of our design rules. We're going to predefine sizes, specify net classes. I already have all my design rules set up, so when you make this example file and you're going to be manufacturing something else for Osh Park, this is the steps you're going to do for your assignment. So import settings from another board, select all, specify the file. So I'm going to import all the rules from this example I did previously. Okay, and then that loads in all my different settings. We have our constraints, and you're going to want to put all these constraints in on your side. And these are the fab manufacturers. This is like the minimum clearance that they can achieve, and Kicad makes sure that when you route all your traces that it's within these minimum bounds. So just copy all these settings. Here's some predefined sizes Sorry about that, but I have them set in standard, and then I've got the vias set in metric. But copy all these track widths. These are your super fine signals, and then these are your high power signals. These are your net classes. Make sure you copy these as well. And we're going to go back and define our net classes in our schematic. So hopefully you got those copied. I'm going to switch units so that it's a bit easier to enter them for the vias. So net classes I defined in millimeters too. So set all these up, pause it now. There's your via sizes in millimeters. And make sure you do them in order because the vias correlate to the track widths. Here's the constraints in millimeter. Okay. All right. So with all of our constraints set up, we're just going to save this for now and exit out of this. And I'm going to teach you guys about net classes. So save. If we go over to the right here, we can define net labels. Oh, we're probably going to have to open it back up again. So close that, reopen it. Oh, there we go. All right, so right here, directive label, we can specify our net class, and that's going to define our trace widths and via sizes. So let's start with power, and then for a 5 volt, I'm going to select power there. And we're just categorizing these connections. So these are all power lines because we're going to be supplying our voltage. And then next, for the rest of them, we can just do standard power traces. If you want, you can do a power line for our LED. Yeah, and then just all these interconnections are just going to be standard connections. Okay. Oh, that one's unnecessary. Make sure not to miss anything. Like this would go undefined and you'd have to go back and place it in. Just a reminder to it's R to rotate. Okay. There we go. Those are all placed out. Save that, and then we're going to go back to our PCB. Okay, so similarly to the schematic, if you want to make it bigger, you can select this and change the paper size. Standard's fine. We are going to update PCB from schematic, so click on that, update PCB, and it gives us all of our footprints for our components all stacked up on top of each other, and then this will give us a general understanding of how big we need to put our PCB edge cut. So just put these right in the center, and then we're gonna go over here and we can select edge cuts. So these are different layers on our board. Here's the copper layer, back copper layer, and all the other associated layers that we discussed in the slideshow. So we're going to be making our edge cut to define our actual PCB area. And we're going to make it pretty big just to make sure we get everything in there. That's a little bit large, so we'll shrink it up a bit. But that should be good. And the next step is we're just going to detangle these blue lines. So these blue lines are the connections that we need to make between our components. And you can see right now they're all over the place, and we're going to want to place these parts to detangle that as much as possible. So just place some stuff out of the way and make sure you have some of the biggest hitters that you're going to place first, because we're going to design these passives around our IC. So first things first, if we zoom in on this, we can see these lines are crossed. So we want to uncross them, so hit R twice, and that completely untangles it. And now we have a straight shot to connecting our components. So if we hit the squiggly line right here to make our routed trace, we can just click it, make our connection, click it, make our connection, and they're completely straight shots. If we rotate our component again and crisscross them, you can see if we go to make one component, make the other connection, now it has to go all the way around. Where similarly, we can right click, place via, go under our component, place another via, and then go around. And that's what I'm talking about, making the shortest possible connection. But we've introduced two vias that are completely unnecessary when we could have just detangled the circuit. So yeah, detangle it, right click twice. I'm just going to put the power pin right here. You can place it wherever you want. And then we'll put our IC kind of in the middle here so we get plenty of space to put components around it. And then we'll put all of our passives. So there we have a tangle, you can see. There we go. So detangle it. Try to keep your crisscrosses as little as possible. There we go. That's a good layout for what we're looking for. Next, we're going to be putting in a ground plane, and the ground plane works as a way to minimize impedance and keep the ground like as close to true ground as possible. It's a good idea to do this on both your layers. Make sure it's not on the layer, because one of the constraints is copper to edge cut, and if you violate that, then the PCB manufacturers will get upset in your DRC. So just click it there, select both of your layers. We're going to define this as ground. Hit OK. And the nice thing about the ground plane is now we don't have to route any of our ground traces, because anything that needs ground will just tie off this plane. Right click, close outline is what I just did there. So a hotkey for this is B, and we can fill the layer up. And so now we have both of our planes selected, and you can click over here on our layers to verify that they're both there. And this is what I was talking about, how they tie off of the ground plane. So now instead of running a trace from this connector up here to our passive, now it just ties into the plane, and this is all just copper. So before, this copper would have gone just unused and sat in the board, but now we're utilizing this ground plane to minimize impedances, and we have 4 solid connections on all of our components. So there's our diode, there's our chip, and we can select between our different layers to see that. Another way to do this is edit and then fill all zones. Okay, so next we're just going to be routing out our traces. So before, we specified net classes, so they're automatically going to be sized properly depending on the net class that you set up. But if you didn't do that, then we can go over here and specify our track width. So if we wanted this super high track, then we can place that, and it'll be super thick, or we can go back over here and place the smallest one, and then you can use the corresponding VIA with that. But we're just going to use the net class because we already have that set up. So following the blue line, the rat's nest, we know that this pin needs to make connection with this IC. So just click it and draw it over here. Now if you don't like the way it looks, you can take it and just drag it around however you like it. So if you want it down here, you can do that. I like that. There you go. And then you just point and click and make all your connections. Oh, see, that seems a little skinny. So if we go over here, let's see if this works. This works on Windows, but it's kind of weird on Linux. So if we click on this, we can see that this connection is a connection made in between these guys, and we made that a standard connection, but maybe that's too small. So just double click on it, and oh, that's what I did. So it's supposed to be medium. Yeah, so change all these to medium. Yeah, that should be good. Save that. And you can click on any component and it will highlight it in the schematic, and that's really nice. Save. So we just made a change. So we're gonna update from our schematic. Okay, and then we're gonna delete these that we put down and then update them with our correct trace size. And you can see up here we're using net class width, and we specified that in the schematic. So now that, see, that's the correct size trace. Make all of our connections. Just point and click. And we can see down here how many unrouted traces we have. So we have 2 more unrouted traces to lay out. And then see, look, we just ran into the problem we were having before, the crisscrossing, and you can't avoid it. So what we do here is we can hit V, or you can right click and put a via, but hit V, through via, V again, and we've gone around that trace. But because this is a through-hole chip and it's not surface mount, we can use both layers. So if we click this back copper layer, we can run a trace on the back piece of copper to make this connection. And it's just a straight shot. Save that, and then we'll go back to our top layer. And we can move around these traces to give ourselves a little bit more clearance. Get rid of any weirdness. So that looks good. Save that, hit B again to refill your zones, and you can see it makes the cutouts for all your traces. And this is one of the constraints set up in your board setup settings right here. So that looks good. This is DRC that I was talking about before. Use this regularly. So click on it. We're going to run DRC and we should get 1 error. There we go. So we got an error because our silk screen is clipped by the solder mask, which basically just means that one of your silk screen references is on top of one of your pads. So you can click this and it'll bring it to you. It'll bring you to it. So it's right here. And you get that little arrow representing the error. So we're just going to take this guy, move it out of the way so you can see it. And then if we rerun DRC, then no more error. Here we go. So if we just get rid of these layers so that you can't see them, this layer that we are on right now is the silk screen, and that's what's going to show up on your actual board, this yellowish. And if we click this little capacitor icon, we can get a 3D view of our board. And we can export this board as a step file so that people can use it to design your enclosure for the PCB. If we wanted to add some holes to actually mount this thing, but also use the 3D viewer to double check your traces and make sure that all your connections are good. And you can actually get 3D files for each one of these components so that you can actually have them show up on your board. So now that we have our completed board, we can export the design files for this. So in order to do that, edit, file, plot, okay, and we're going to specify our output directory where we want our manufacturer files. So just make a new folder. You can name it whatever you want. Okay, and then go to generate drill files and make sure that your output is the same. Generate, you don't have to mess with any of these settings. And then hit plot. Okay, close this, and then now you should have all of your files generated. So go to where you did that, and then compress it to a zip file. We can go to Oshpark's website, browse for files, and then submit your zip file that you just did. And then once your files are uploaded, you can double check your design files. Oshpark forces you to double check everything. So just go through it, and this is what your board's going to look like. And make sure all your drills are good, and your footprints look good. Make sure any of your traces aren't like connecting, so you're not shorting something. And you can hit order. Okay. So next we are going to design a symbol and a footprint for our 555 timer. So go to symbol editor, and then we're going to pull up the data sheet for a 555 timer. I'm using the ICM 7555 IPA. You can find the data sheet on DigiKey. So here's our chip. We're going to be assigning pins to this specified by the data sheet. So first create a new library. Make it global. Save it wherever. A new symbol. Okay. Make sure you name the symbol by its part number. Okay, and there's your reference designator. Okay, so first thing you're going to want to do is assign all your pins. So with your data sheet pulled up, this one's better. We're going to label all these pins and give our symbol like a basic box shape. So, what we'll do is we'll actually replicate this symbol so we can just plug it in. Okay. So let's place our pins. Pin name, GNB, pin number 1. And we want these circles facing out, because if you remember in our schematic design, that's what we're actually tying off to. And just go around and name them all. I'm gonna have to rotate this one because it's on the other side. And I'm just doing this connection because it's, or like this pin layout, because this is what the data sheet specifies, but you can do it in any way you want. Some people specify the power connection on top and then group the pins by like functionality instead of just what they are on the pinout. But for this, it just is easier to do the pinout. Okay. And we'll just reshuffle everything here. Oh, it looks good. Move this designator out of the way. Okay, and we'll just draw a little box to represent our symbol. There we go. And that's our symbol, and we can define these pins by functionality. So for ground, we have input, but we can specify it as bidirectional, passive, output, power input. So we'll just leave ground as input for now, but we can specify this one as a power input. There we go. And you can do that for all your pins depending on the functionality. So hit save. Okay, and now we have our symbol for this specific IC, so that we can go back. Oh, wrong one. We can go back to our schematic editor and we can import the symbol we just made. We can put it in here, and you can replace our existing symbol. I'm just going to leave the symbol that we already have put in, but you can make the connections and it would virtually work the same. Okay. So next, we're going to make a footprint. So go to our footprint editor. Here. And we're going to scroll all the way down, and in order to make our footprint, we're going to want our mechanical information. Most of the time they just have it inside the data sheet, but in this one it's a separate hyperlink. So we're going with the 8 PDIP package style. So we'll just click on that. And this is the mechanical sheet for our PDIP package. And it has everything that we need to recreate the footprint. I already figured out all the coordinates and where you need to place everything, so I'm just going to walk through it. But just a basic gist of what's happening is, in our footprint editor, we have our coordinate system for Kicad, and each pin is going to be placed on this coordinate system. This is the positive X direction, and this is the positive Y direction, and positive Y goes down because the coordinate system for Kicad is just inverted. You can make this part as easy or as hard as you want to. I like to assign my first pin to be 0, 0 on the coordinate system and then go out from there. It's worth sketching out your IC and then placing each via on this coordinate system and figuring out where you need to make it, so you can just go in here and make that adjustment. This is a standard 2.54 millimeter pitch that you'd use on a breadboard, and so we can go in here and double check that. So for our pitch, it's lowercase e. So if we walk over here to our lowercase e and go to millimeters, 2.54, and then we're going to be placing our vias as through holes so that we can actually mount this chip on the board, and we need to know how big the drill hole is for the via and how big the pad size is that you're going to be soldering onto, and this is where IPC comes in. So as a general rule of thumb, whatever the lead size is for this IC, we're going to be adding 0.25 millimeter. That's a good rule of thumb for doing through-hole designs or any just SMD design. So for this specific board, if we go to B, that's the lead size for this chip. And we're going to be going to the worst case scenario. So the worst case scenario is 0.56. So 0.56 millimeters, and then you add 0.25 millimeter for the lead hole, and that gives you the drill size for your through hole. For your pad size, just add 0.8 millimeters on top of your hole that you made for your lead, and that should give you enough pad space to actually solder onto. That gives you 0.4 millimeters on either side, and this will be more clear once I actually start placing stuff down. So first, let's figure out where we are in here. Oh, there we are. Okay. So I don't think we've done this yet, but let's make a new library. Or we can just use a pre-existing library. Use a pre-existing library. So I won't make a new one. Alright. Global library. Name it our specific chip. Okay. And then select it. Create new footprint. There we go. So right now it's named unentitled, so just right click on it. Oh, we don't want to duplicate it. To rename it. Okay, rename it, boom. There we go. That way you can find it when you actually go to assign your footprints from your schematic. The first thing you're going to want to do is place all your pads. So just go around and place all your pads. We have 8 of them. Doesn't matter where you put them because we're going to assign them later anyways. But you can put it in a general shape that we're going to go for. Okay, so then for each one of these pads, we're going to assign it its coordinate system, and we're going to assign it the type. So here we have pad number 1. Right now it's SMD, that's why it's just like a square top layer piece of copper right here. We're going to change that to a through hole. We're going to go circular. And then we're going to go to each of these and specify this. It's going to be it's going to have a hole size of 0.8 millimeter, which is what we got from adding 0.25 to 0.56 over here in our mechanical diagram. And then our pad, and the hole size is like the actual hole that goes through the board. And our pad size, we're just going to add 0.8 on top of our hole size, and that's going to give us 1.6 millimeters. And that's the pad size around the hole, and that gives you plenty of space to solder onto it. Next, we're going to be placing this through hole on our coordinate system. So I already have the math figured out on this, but like I said, pin 1, just keep it 0, 0 for simplicity. Hit OK, and then you can see it gets lined up. You can also specify where like the global 0 is on your coordinate system, so that's worth keeping in mind. So now it's just kind of tedious. I'm going to go through and assign each of these to be a through hole, a circle, specify the coordinate system, and this one's pretty easy because it's just breadboard rules. So because these are all in line, we're not moving anywhere on the x-axis, and because the pitch is 2.54, we're just going down by 2.54. There we go. See, it's right where we need it to be. 0, and then 2.54 times 2. So to get this X position, what I did was I took EA, which is like the leads after you kind of squish them inwards a little bit. So that's 7.62. So I know it's 7.62 to the right of where we're at. And keep in mind that the y-axis is positive because we're going down on the coordinate system. There we go. Almost done. There we go. So this is our pad layout using the mechanical diagram. Everything's good. Double check your measurements using this little measuring tool right here. Yep, it looks good. So next we're going to specify the courtyard, which means that no components can be placed within this part. Without the courtyard, then you could just place like a resistor right on top of your part, which wouldn't work well. So go over to your different layers. We'll go to front courtyard and hit the rectangular tool and just draw a rectangle. Okay, and then the way I defined this courtyard is by defining like the size of the P-dip itself and then using that as the courtyard. So the distance, and then make sure you pick the max. Always go max, worst case scenario. And then I extended a little bit out from these pins to get the coordinates. So double click on that and we can specify the start point and the end point. So for our start point, we have negative 0.39. And then for our y-axis, negative 0.2, negative 2.03. Endpoint 8.01, and then for our y-axis 9.65, and then that gives us our courtyard. So now we can't place any parts inside of this. Next, we're going to want to figure out, we're going to want to place references to make sure that this is going to be pin 1 when you actually go to solder it up, so that you don't actually solder on this thing backwards. So double click pin 1 and we can make this thing rectangular, and that's a good designator right there. But we can go one step further and draw on the silk screen to get our part. Now we don't want to go and clip through these pads, so try to stay away from the pads. We can place a silk screen. Oh, actually we'll go right to the courtyard for this one. There. There we go. And then we can select the arc tool. Go to our midsection, and this is another like reference designator. Draw that. Then we're going to make another arc. Go around right there. There you go. So then now you have another reference. And I mean, oh, we can delete that and then draw our silk screen box again. Sure we keep it 90 degrees. There we go. So now we have a silk screen box and we've got our little reference designator to make sure that we're on pin 1. And we can now just hit save. And now we can use our footprint in our actual PCB editor. So we go back to our PCB editor, can import footprint. There we go, that's the one we just made, and you can use it in place of this one. In order to use it in place of it, of the one we have like existing, then we can go to our schematic, go back to the symbol like assigner for the footprints. Click on this one and just find your package over here. Another good tip for assigning footprints is you can use these filters to narrow down your search. So you can filter it by pin, and that gets rid of a lot of different options, and you can filter it by library. So if we wanted to look right here, then we only get the footprints with 8 pins and all the footprints in this specific library. Okay. So with that, you should have everything you need to create simple PCBs in Kicad. Have a good day.